All right, picture this. You're drowning in information, but you need to understand something complex, fast. You want the core insights, the surprising facts, the stuff that actually sticks, without having to read through a library yourself.
Exactly.
That is exactly what we are here to do. Welcome to a deep dive into a fundamental, often hidden process in manufacturing and metal finishing. Barrel plating. It's the workhorse method behind countless everyday items you interact with, but the details of how it makes things shiny, durable, or resistant to rust are usually tucked away.
Yeah, you don't really think about it most of the time.
Not at all. Now, we've pulled together a really interesting stack of sources for this deep dive. We've got foundational info from a blog post by American Plating Company giving us the essential benefits and basics.
That's a good starting point.
Yeah. There's a YouTube transcript from Master Finish Co., which is great because it helps us visualize the actual process. See it in action, sort of.
Right. Gives it some context.
We also have some deep technical background and historical context from P2 Info House, drawing on experts like Raymond Singleton and referencing equipment leaders like Upton and Singleton Corp.
So some real heavy hitters in the field.
Definitely. To understand why you'd pick this method, we've got insights from Accurate Precision Plating and Microfinish, specifically contrasting barrel with rack plating.
Ah, the classic comparison. That's crucial.
Exactly. We'll troubleshoot with help from an Everest Machinery blog on common electroplating problems. And we even get a peek into the underlying chemistry with a practical guide to DIY nickel plating from Instructables, though, with a massive caveat, which we'll definitely get to.
Oh, yeah. The DIY stuff always comes with warnings.
Big time.
Okay.
Finally, a crucial dose of reality from a nickel plating solution SDS by Nano3D Systems, and a smart checklist on the strategic decision of pre versus post plating from Engineering Specialties, Inc.
It really is a comprehensive collection, touching on the commercial drivers, the technical specifics, the hands-on reality, and critically, the safety considerations. Our goal, our mission, is to take all of this diverse information, sift through it, and pull out the absolute most important nuggets of knowledge and insight about barrel plating for you.
Right.
We're going to understand its core principles, why it's such a prevalent technique despite its limitations, what those limitations are, and the common challenges involved. It's all designed to give you a clear, informed perspective on a process that touches so many manufactured goods.
All right, let's jump in and get to the heart of it. What exactly is barrel plating? If I walked into a facility, what would I see and what's fundamentally happening?
Okay, so at its core, barrel plating is a method designed for processing large quantities of small parts in bulk. That's the key takeaway.
Bulk processing, got it.
Instead of hanging items individually, you load them into a special container, the barrel. This barrel, essentially a large, often perforated drum or cylinder, holds the parts and is rotated while it's immersed in a series of chemical tanks.
Okay, so it's about volume, processing many items at once. And the rotation of the barrel is key.
Absolutely critical. As the barrel slowly turns through the tanks, think of it like a washing machine, gently tumbling clothes, that kind of motion.
Okay.
The parts inside tumble and cascade over each other. This continuous motion ensures that all surfaces of virtually every single part are exposed to the chemical solution, whether it's a cleaning bath, a rinse, or the final electroplating solution.
Got it. And in the plating tank, that's where the magic happens, driven by electricity.
Precisely. In the electroplating bath, which contains dissolved metal ions, an electrical current is passed through the solution. The parts inside the barrel act as cathodes, the negative electrodes.
Right.
And this negative charge attracts the positively charged metal ions dissolved in the solution. As the parts tumble and make electrical contact inside the barrel, which is a whole other thing we'll get into, the metal ions deposit themselves onto the surface of the objects, forming the desired coating.
So it's that combination of bulk loading, continuous tumbling for exposure, and the electrochemical process for deposition. That makes sense.
Exactly.
It sounds like an ingenious way to scale up the plating process.
Huh.
And this isn't a recent invention, is it? The sources mention its history.
That's right. This bulk processing method isn't some cutting-edge 21st century technique. The sources trace its origins back quite a ways, specifically to the post-Civil War era in the United States.
Seriously. Post-Civil War. That's much older than I would have guessed.
Oh,
What was the equipment like back then? Must have been basic.
Very rudimentary compared to today. The early equipment often utilized actual wooden barrels or even kegs as the rotating containers.
Actual wooden barrels. Wow.
Yeah, this made the method relatively accessible and lower in cost at the time, which, contributed to its adoption for processing hardware and other small goods.
Wooden barrels rotating through chemical baths sounds challenging to maintain consistency, and it probably didn't last long.
Indeed. Chemical resistance was certainly a limiting factor, I imagine. Fast forward to today, and modern barrel plating equipment is constructed from highly durable, non-conductive, and chemically inert materials, with polypropylene being a common choice.
Polypropylene, okay.
These materials can withstand the aggressive acids, bases, and high temperatures used in modern plating processes, allowing for much greater consistency and longevity of the equipment.
Okay, so we know what it is. A bulk tumbling electroplating method developed long ago but using modern materials now. But why do we even bother plating things in the first place? What are the core functions that metal plating serves on manufactured goods?
Right, good question. Plating serves several fundamental purposes that add value or functionality to a base material. The first, and arguably most common application, is corrosion resistance.
Stopping rust, basically.
Exactly. Many base metals, like steel, will rust or corrode when exposed to the environment. Applying a thin layer of a more corrosion-resistant metal like zinc, nickel, or cadmium sacrificially protects the underlying material, making the finished product last significantly longer. This is crucial in everything from construction fasteners to automotive parts and even food processing equipment, where preventing rust is vital for hygiene and longevity.
Like the dull gray or sometimes yellowish coating you see on many bolts and screws.
Exactly. That's often zinc, or maybe chromate over zinc. The second function is purely decorative.
Making things look pretty.
Pretty much. Plating is used to enhance the aesthetic appeal of an object. This could be applying a bright, shiny finish like chromium or bright nickel for visual appeal, giving objects that dazzling gleam you see on faucets, door handles, or automotive trim.
Right, the bling factor.
Chuckles slightly.
Yeah.
But it can also provide other appearances, from brushed finishes to specific colors or even metallic black coatings, as mentioned in some sources for nickel plating applications.
So making things look good, what's a third major purpose?
The third is for engineering or functional properties. Plating isn't just about looks or corrosion, it can add specific physical properties to the surface.
Okay, like what?
This includes increasing surface hardness and durability to resist wear and tear, improving conductivity for electrical components, making it easier to solder to difficult-to-join metals, or even adding magnetic properties with thicker deposits of certain materials. Electroless nickel, for instance, is often used for its uniform thickness and hardness in engineering applications.
So plating can make a part harder, easier to solder, more conductive. It's modifying the surface properties for specific tasks.
Precisely. You're tailoring the surface of a material to a specific requirement that the base material might not meet on its own.
Given those three big buckets, corrosion, decoration, and engineering, where does barrel plating fit best? Is it good for all three?
Well, while plating in general addresses all three, the sources indicate that barrel plating is most commonly employed for corrosion protection and decorative finishes, particularly where the aesthetic requirements are important but can tolerate the slight variations inherent in a tumbling process. It's less frequently the go-to method for demanding engineering applications that require extremely tight control over plating thickness and distribution on specific critical surfaces.
Why is that? Because of the tumbling.
Yeah, because the tumbling action means you can't fixture a part precisely in one orientation relative to the anodes, the electrical source, and the tank.
That makes sense. If you need an absolutely perfect, uniform coating of a precise thickness on a critical dimension of a complex part, individual fixturing on a rack probably gives you more control.
That's right. That's where rack plating comes in. But for the vast majority of small parts needing protection or a decorative finish, barrel plating is highly effective.
And it works with lots of different metals.
Oh yeah, it's versatile enough to be used with a wide range of plating chemistries, including gold, tin, silver, brass, nickel, and copper, as noted by American Plating Company. Other sources broaden the list to include electroless nickel, electrolytic plating, zinc, cadmium, and even some chrome applications in specific barrel setups, though chrome is generally more challenging in a barrel.
That's quite a spectrum of metals you can deposit this way. So if you have a large batch of small, durable parts that need plating for corrosion or decoration, why would you almost certainly choose barrel plating over other methods like rack plating? What are the overwhelming advantages?
The single biggest driver, the overarching benefit that makes barrel plating so ubiquitous for suitable parts, is significantly higher efficiency. It's simply a far more productive way to process high volumes, hands down.
Efficiency how? In speed, cost, labor, or all of it?
Pretty much all of the above. Firstly, it enables large, rapid volume production. Because you can load hundreds, thousands, or even tens of thousands of small parts into a single barrel simultaneously, it's vastly faster for production compared to individually hanging each part on a rack.
Right, just loading one barrel versus maybe hundreds of rack fixtures.
Exactly. It is the definition of efficient bulk processing. This bulk handling also means it requires less floor space to process the same volume of parts compared to setting up extensive rack lines.
Makes sense. More compact.
The equipment investment is typically lower for a barrel line designed for high volume than for a comparable rack line. And most significantly, it requires substantially less labor.
Less labor because you're not manually handling each individual piece over and over.
Exactly. Think about the labor involved in carefully attaching every single screw or nut onto a rack, moving that rack through multiple tanks, and then detaching each piece. It's tedious.
Very tedious.
In barrel plating, you load the parts into the barrel, and the entire cleaning, rinsing, and plating sequence often happens with the parts staying inside. This means you might only need one person to operate an entire barrel line, especially with automated systems, whereas rack plating requires numerous operators just for loading and unloading.
Wow.
P2 InfoHouse highlights this as a major ongoing cost advantage, eliminating the expensive labor of individual part handling between operations.
I can see how the labor savings alone would be enormous for high-volume manufacturers. That's huge.
Absolutely, and automation takes it even further. Systems like those described by Master Finish Co. use programmable controls and automated hoists, sometimes laser-guided, to move the barrels through pre-programmed sequences with precise dwell times and rectifier settings.
Laser-guided hoists.
Yeah,
Yes.
it gets quite sophisticated. This eliminates human handling errors and variations, delivering incredibly consistent and efficient results with minimal labor input. Upton is mentioned as a supplier of such automated and manual equipment. All of these factors, speed, space, equipment cost, and especially labor, contribute to barrel plating being consistently presented as a lower-cost alternative compared to rack plating, particularly for decorative finishes where the slight cosmetic trade-offs are acceptable. The economic advantage is often compelling enough to make it the preferred method, even if there are some process limitations.
Okay, so the efficiency and cost benefits are huge for mass-produced goods. What about the finish itself? How does tumbling affect the final coating? Does it scuff things up?
That's a good question. Interestingly, the continuous cascading motion of the parts in the barrel actually helps to produce a relatively uniform metal finish across the batch. As parts tumble and rub against each other, it can have a slight polishing or burnishing effect.
Ooh, really? Like a rock tumbler?
Kind of, yeah. And it helps ensure that fresh plating solution is constantly reaching the surface of every part. This action also creates agitation in the tank solutions, which is beneficial.
How so?
It helps prevent the plating chemicals from stratifying or settling, promoting a more homogeneous bath chemistry throughout the tank, which in turn contributes to more consistent plating results from part to part and batch to batch.
Keeps the soup mixed well.
Exactly. The tumbling also actively prevents parts from sticking or nesting together, which would otherwise lead to unplated or poorly plated areas.
So the tumbling isn't just about exposure, it's also about maintaining bath chemistry and preventing parts from clinging together and shielding each other. That's clever.
Precisely. It's an active part of creating a consistent environment within the barrel. Beyond that, barrel plating is incredibly versatile in terms of the types of parts it can handle simultaneously. While there are limitations on size and fragility, within the suitable range, you can plate many different shapes and sizes together in one barrel.
Unlike rack plating where you need specific holders for specific parts.
Right. Rack plating might need specially designed forms or fixtures for different part geometries. Barrel plating adapts to a greater variety of parts and production capacities more easily.
All right, that paints a clear picture of the why, massive efficiency, lower cost, versatility, and a reasonably uniform finish for suitable parts.
Yeah.
So when wouldn't you use barrel plating? When does rack plating become necessary or preferable?
Rack plating is the method of choice for parts that are either large or fragile. If you put delicate components or large, heavy items into a tumbling barrel, they would likely be damaged. Simple as that.
Makes sense. Don't want to break things.
Rack plating allows you to gently fixture each part, protecting it from impact. It's also essential for parts requiring an extremely high-quality cosmetic finish or very precise control over plating thickness on specific surfaces.
Right, the really perfect-looking stuff.
Yeah. When a part is individually hung on a rack, its position relative to the anodes and the bath chemistry can be tightly controlled, allowing for highly uniform and precise plating, crucial for visible consumer goods or parts with critical engineering dimensions.
Think of a large, shiny, sculpted car emblem, or maybe a sensitive electronic component that needs micro-inch plating in a specific spot.
Exactly. Those are rack jobs. Rack plating allows that level of meticulous control and protection. So while barrel plating is best for small, durable components that can be processed in bulk or those with configurations that are tricky to hang individually, rack plating steps in for the large, the fragile, the geometrically challenging, or the cosmetically perfect.
Got it. Switching gears from the why, let's get into the how. What does the actual equipment look like, especially the barrels themselves, and how do they facilitate this complex process?
Okay, so modern barrel plating equipment, as we discussed, is built from robust inert plastics like polypropylene. The design of the barrel itself is critical, and there are a few variations described in the sources.
What are the main types?
The most common type, the real workhorse of high-volume barrel plating, is the horizontal barrel. These are cylindrical or sometimes multi-sided drums that rotate a full 360 degrees while submerged in the plating tanks.
Okay, the standard rotating drum we picture.
Right. They can be designed for maximum load volumes within the size constraints of the tanks and hoists, and some incorporate features like automatic doors to speed up loading and unloading, making it even more efficient.
Automatic doors? Neat. Are there other types?
Yeah, less common these days are horizontal oscillating barrels. These are open at the top and don't rotate fully. Instead, they rock back and forth through a limited arc, maybe 180 degrees.
Just rocking back and forth.
Yeah. This rocking motion is gentler, which can be suitable for slightly more delicate parts than a full rotation barrel can handle. However, the tumbling action is less vigorous, and the open top limits the load size and, potential for solution carryover issues.
Okay, and the third type?
A third type is oblique barrels. These rotate around an axis that's tilted up to about 45 degrees from vertical.
Tilted barrels.
Yeah. Like oscillating barrels, they are typically open at the top, eliminating the need for doors. The tumbling motion here is also less vigorous than in a horizontal barrel, generally resulting in smaller maximum workloads.
So horizontal barrels dominate for their capacity and effective tumbling, it sounds like. The sources also talk about optimizing barrel design itself for performance and maintenance, right? Not just the type.
They do, and it's a key point for operational efficiency and cost over time. Proper barrel design should aim to minimize the need for replacing the entire barrel assembly due to wear on a single component.
How do they do that?
The sources advise avoiding integral wear parts, things like hanger arms or cylinder gears that are molded directly into the barrel ends, because if those wear out or break, you have to scrap the whole barrel.
Right. Replace the whole expensive unit for one small part.
Exactly. It's much more cost-effective if components like the electrical contacts or drive gears can be replaced individually. Modular design, basically.
Smart. What about the materials and temperature?
The materials used in construction are also vital. Barrels must withstand the maximum operating temperatures of the plating baths over continuous use, and, importantly, avoid using construction materials with significantly different coefficients of expansion in the same assembly.
Why is that?
Because temperature fluctuations in the tanks can cause these materials to expand and contract at different rates, potentially leading to stress, warping, or even structural failure over time. It's a subtle but important detail.
That's a hidden complexity, how temperature affects the barrel itself. What about the shape of the barrel cylinder? Does that matter for tumbling?
Yes, the internal shape affects tumbling. Flat-sided barrels, as opposed to perfectly round cylinders, are generally considered better for promoting proper tumbling action and preventing parts from sticking flat against the inner wall.
Flat sides help lift things.
Yeah, the flat sides lift the load and encourage it to cascade more effectively. Round barrels lack this pumping action, although adding tumbling ribs or crossbars inside can help improve agitation and prevent parts from just sliding in a mass.
Okay, the barrel has holes in it, so the solution can get in and out. How is the size of those holes determined? Seems critical.
Oh, it's absolutely critical. The size and configuration of the perforations must be specified based on the smallest parts you intend to plate. If the holes are too large, well...
Your parts fall out.
Exactly. You lose your product. Job shops that handle a wide variety of part sizes often need barrels with smaller hole openings to accommodate their diverse customer base. Captive shops, pleating only their own parts with a predictable minimum size, might opt for larger holes.
And larger holes offer advantages, assuming your parts are big enough not to fall through.
Absolutely. Larger perforations facilitate faster drainage as the barrel lifts out of a tank, which reduces solution carryover or drag out into the next tank.
Less mess, less contamination.
Right. They also allow for easier and quicker exchange of the plating solution between the outside of the barrel and the inside where the parts are tumbling. This rapid exchange helps prevent the solution inside the barrel from becoming metal depleted right around the parts, ensuring a consistent supply of ions for plating.
So better solution flow.
Better flow, less drag out, less contamination. It's a big operational plus. The sources also point out that if you have multiple barrels running on the same line, ideally they should have the same open area ratio.
Open area ratio, what's that?
It's the ratio of the total area of the perforations to the total surface area of the barrel panel. Keeping this ratio consistent across different barrels allows you to use barrels with different specific hole sizes as long as they hold the parts interchangeably on the same line without needing to constantly readjust the rectifier or current settings. It simplifies process control.
Ah, okay. Consistent performance even with different hole sizes.
Exactly. And for extremely small or unusually shaped parts like very small pins, needles, or electronic components, special perforation configurations are available, including herringbone patterns, fine screen inserts, or narrow slots designed to hold these specific geometries.
That makes sense. Now, how does the electricity actually get to the parts tumbling around inside? That seems like a logistical challenge.
It is a key design challenge for barrel plating, absolutely. Since the parts aren't individually clipped to a conductive rack, electrical contact is made inside the barrel itself. The most common and widely used type of internal contact is flexible danglers.
Danglers, like thick wires hanging down.
Yes, often made of conductive materials, sometimes covered with protective insulation except at the tip. They hang down into the tumbling mass of parts. The sources emphasize that to get the best plating results and prevent issues like arcsing or burning, these danglers must be properly submerged within the workload of parts.
So they need to be deep in the pile of parts.
Exactly. If they're just floating on top or making intermittent contact as the load shifts, you get inconsistent current distribution, which leads to uneven plating.
Are there other types of contacts besides danglers?
Yes. Besides danglers, various stationary contact types are used depending on the part type and barrel design, including disc, strip, center bar, cone, button, chain, or star-shaped contacts. Plate-style contacts are more often seen in oblique barrels.
A whole range of options.
Yeah. The goal is ensuring positive, continuous electrical contact. That's crucial for efficient operation, especially when running at high amperage to achieve faster plating rates. The sources also note that using plastic non-conducting hanger arms on the barrel helps prevent unwanted metal deposit buildup, known as treeing, on the barrel's external structure.
Treeing, what's that? Sounds weird.
Treeing is when, due to uneven current distribution or stray currents, the plated metal starts depositing not as a smooth layer, but in branching tree-like formations, often growing towards areas of higher current density.
Like little metal trees growing on the equipment.
Sort of, yeah. It's unwanted metal buildup that wastes material and can cause problems like short circuits or mechanical interference. Plastic arms on the barrel prevent them from accidentally becoming cathodic and attracting this treeing.
Got it. Like unwanted branches growing where they shouldn't. How is the electrical current density controlled for the whole barrel load, making sure enough power gets there?
Good question. Current density, which directly affects the plating rate and quality, is maximized by placing the tank anodes of the positive electrodes in the plating bath as close as possible to the barrel exteriors.
Get the power source close to the target.
Right. For horizontal barrels, using anodes that are contour curved to match the barrel's circular profile can significantly increase current density by maybe 10–20%, according to P2 InfoHouse, because it minimizes the distance the current has to travel through the solution. More efficient power delivery.
We touched on automation earlier, but let's go a bit deeper. How do these automated systems tie all the pieces together? The hoists, the recipes.
Right. Fully automated barrel lines, like those from Master Finish Co. or Upton, are pretty sophisticated systems. They use programmable logic controllers, PLCs, and computer interfaces to manage the entire process sequence. Features include things like laser-guided hoist positioning for incredibly precise movement of the barrel from tank to tank.
Lasers, okay.
And pre-programmed recipes.
Recipes, like for baking cookies.
Chuckles. Not quite, but similar in concept. These recipes are computer programs that dictate every step for a specific type of part or plating finish. The exact travel path of the hoist, the precise dwell time the barrel spends in each tank, cleaning, rinsing, activation, plating, post-treatment, the specific rotation speed of the barrel, and critically, the exact rectifier settings, so voltage and current, applied in the plating tank.
So total process control programmed in.
Exactly. This automation eliminates human judgment and potential for error at each step, delivering highly precise, consistent, and efficient results without hands-on labor for transferring loads. Fully automatic load-unload systems can even add parts to the barrel and empty them out without manual intervention, a completely hands-off operation.
Wow, that's impressive integration. What about other design features, like
What were you-
safety or drainage?
Yeah, other system design considerations include maintaining the solution level in the tanks. Tanks are often designed so that when the barrel is immersed, the solution level is approximately 5 inches from the top rim of the tank.
Why that specific distance?
This ensures the entire barrel cylinder is fully submerged. Keeping the barrel completely underwater minimizes the chance of excess hydrogen gas accumulating in any unsubmerged headspace inside the barrel cylinder. This reduces the potential for hazardous gas buildup, especially in processes that generate a lot of hydrogen, which can be explosive.
Safety built right into the tank design. Smart. What about getting the solution out of the parts after plating? Drainage sounds tricky with a barrel full of small items, especially complex shapes.
Drainage is crucial to minimize drag out, the unwanted carryover of solution from one tank to the next, which contaminates baths and wastes chemicals. Some automated hoist systems include an up barrel rotation feature.
Up barrel rotation.
Yeah. As the hoist lifts the barrel clear of a tank, the barrel continues to tumble the load overhead. This helps parts trapped in cups or recesses to drain more effectively back into the tank they just left.
Shakes the liquid out.
Essentially, yes. And as we mentioned, larger perforations in the barrel also significantly improve drainage speed and efficiency.
Okay. And you mentioned the drive unit needing adjustment.
Right. A final detail on the mechanics. On horizontal barrels, the tank drive unit, the motor that rotates the barrel when it's in the tank, needs careful vertical adjustment. It has a gear that meshes with a gear on the barrel. You need to adjust its height to get maximum gear engagement for reliable rotation, but if it's set too high, the drive unit can end up carrying some of the weight of the fully loaded barrel assembly.
Which it's not supposed to do.
Exactly, that's not its job, and it can disrupt the crucial electrical contact made through the barrel hangers. So it's a fine adjustment.
It sounds like a lot of precise engineering goes into even the movement and positioning. Now, you've mentioned repeatedly that barrel plating is best for suitable parts. What characteristics make a part a good candidate and which ones make it unsuitable? Let's nail that down.
Right. The suitability of a part for barrel plating is really a multi-factor decision based on the desired finish function, the part's geometry, size, weight, surface area, and importantly, the specific barrel equipment available. Generally, simple shapes are the easiest to plate successfully in a barrel.
Like what kind of parts?
Common examples are mass-produced items like bolts, nuts, washers, stampings, forgings, or castings. You know, the bread and butter of hardware. For threaded parts like bolts and nuts, sufficient tumbling is absolutely essential to ensure uniform coverage, not just on the outer surfaces, but also down in the root, on the mean diameter and the crest of the threads. If they don't tumble well, those areas won't get consistent plating.
Okay, what about parts that aren't simple or might tangle, like long, skinny things?
Yeah, parts that tend to entangle or are long and slender like rods, bars, or tubes can still be barrel plated, but it often requires specialized equipment or techniques. This might involve using extra long barrels, barrels with internal compartments to separate parts, incorporating a rocking or oscillating motion instead of full rotation, or using special contact types designed for these geometries.
So there are workarounds for tricky shapes.
There are. Lightweight, flat parts can sometimes stick together, like coins, shielding surfaces. The sources recommend plating these in barrels with convoluted, meaning not smooth and flat interior surfaces to promote better tumbling and prevent sticking.
Got it. And parts with holes or cups.
For parts with deep recesses or internal cups, sometimes smaller parts are mixed into the load. These smaller pieces can help tumble into the recessed areas, improving solution exchange and providing better electrical contact. However,
Have to separate them afterward.
exactly. You then need a way to easily separate the mixed parts after plating, which can be a logistical challenge. Adds another step.
Is there a general size or weight limit?
A general guideline from the sources is that individual parts weighing less than 1 pound and with a volume of less than 25 cubic inches are typically well suited for barrel plating. But again, it depends heavily on the part's durability and geometry. Small, durable components are ideal.
So, small, durable, and generally simple shapes are ideal. The opposite would be large, fragile, or complex parts needing precise finish.
Precisely. Fragile parts will get damaged by the tumbling. Large parts are difficult to load efficiently and don't tumble well in bulk. And parts needing an utmost high-quality cosmetic finish or super precise dimensions are better off with the controlled fixturing of rack plating.
This leads us to another critical decision point, highlighted by Engineering Specialties, Inc. Whether to plate the raw material before you fabricate the final part, or plate the finished part after fabrication. Pre-plating versus post-plating. That sounds important.
Oh, it's a huge strategic decision for manufacturers, driven primarily by cost, desired performance, and appearance. Pre-plating involves taking the raw material, like a large coil or sheet of metal, and plating it before it's cut, stamped, formed, or otherwise fabricated into the final part.
What's the main draw there? Why do it first?
The primary benefit, hands down, is low cost. It is significantly quicker, easier, and less expensive to plate a continuous roll of material than to handle and plate thousands of individual finished parts, especially if those parts are complex shapes that would be difficult to post-plate efficiently, even in a barrel.
But that sounds like there must be trade-offs.
Yeah.
Big ones.
Significant ones, yes. The major disadvantage is that any areas that are cut, stamped, or formed during fabrication will be left unplated.
Ah, so the edges are bare metal.
Exactly. This means edges, holes, and cutaway sections have no plating protection. This drastically reduces the corrosion resistance of the final part, making pre-plating unsuitable for components exposed to harsh or corrosive environments. If the part design involves extensive cutting or shaping, a large portion of the final surface could be unprotected.
So great for cost, potentially terrible for corrosion resistance at the edges.
That's the trade-off. The appearance can also be less uniform compared to post-plating, and parts that require heat treatment after fabrication usually need post-plating because the high temperatures can affect the pre-plated layer's integrity.
All right, then post-plating is the alternative. Plating after the part is made.
Yes, post-plating means the plating process is performed on the finished part after all fabrication steps are complete.
What's the advantage of doing it last?
The main advantage is that it guarantees the entire part is fully coated, including all edges, cut surfaces, and complex geometries. This is essential for parts exposed to harsh conditions where corrosion on any surface is unacceptable, or for visible components that require a flawless, uniform, polished appearance. Complete coverage.
That sounds more robust and higher quality. What's the downside? More expensive.
The main drawback is higher cost. Handling individual finished parts or even processing them in batches in a barrel is more labor-intensive and generally slower than plating a continuous coil of raw material. There's also a potential risk of dimensional issues if the plating thickness isn't precisely controlled, which can be a concern for parts with very tight tolerances. Adding that layer changes the size slightly.
Right, the plating adds thickness.
Exactly. A crucial point mentioned by the sources, relevant to both methods, is that plating won't fix surface imperfections on the base material. You're applying a coating, not resurfacing.
Garbage in, garbage out, basically.
Pretty much. If the raw material is rough or scratched, the plating will likely show those flaws or even amplify them. The starting surface should ideally be smoother than or match the desired final finish.
That's a vital point. Plating is an additive process, not a smoothing one. You start with a good surface to get a good finished product. Let's get specific and talk about a very common type of plating often done in barrels: nickel plating. The sources provide some unique insights here, including a glimpse into a DIY approach and, critically, a very serious look at the potential hazards involved.
Right. Nickel plating is frequently performed using barrel methods, especially bright nickel plating. This process is popular because it delivers excellent corrosion resistance and provides that highly desirable, bright, lustrous, almost mirror-like appearance. Very common finish.
The Instructable source is fascinating because it details how someone might attempt nickel plating at home. While obviously not industrial scale, it's a great way to understand the fundamental chemistry and electricity involved, stripped down to basics.
It really is illustrative. For a DIY setup, they describe creating a plating solution, the electrolyte using relatively common materials, distilled vinegar as the acid base, table salt to increase conductivity, and a source of pure nickel, like a piece of pure nickel metal.
Vinegar and salt. Seriously.
Yeah, for a simple acetate bath. They also use a DC power source, recommending a power supply over just batteries for stability and duration.
And how do they get the nickel into the solution to start with? You need nickel ions, right?
Right. They use a process called electrodissolving. You connect one piece of pure nickel to the positive terminal of the DC supply, that's your anode, and another piece, or perhaps the object you'll eventually plate, to the negative terminal, the cathode.
Okay.
When you apply power in the vinegar salt solution, the positive nickel electrode slowly dissolves, releasing nickel ions into the solution. You see bubbles forming oxygen and some chlorine at the positive, hydrogen at the negative. As the nickel dissolves, the solution gradually turns a light green, indicating the formation of nickel acetate.
So the solution color tells you it's working.
Generally, yes. They note that if the solution develops other colors or becomes cloudy, it's a sign of impurities in the nickel source you used.
So even in a simple DIY setup, the purity of your materials is crucial.
Absolutely, just like in industry. And preparation of the object to be plated, the cathode, is paramount. Same principle applies. Like industrial plating, it must be scrupulously clean, free of any grease, oils, oxidation, or grime.
Clean, clean, clean.
The guide suggests cleaning with dish soap, abrasive cleaners like Cameo, or even briefly using reverse electroplating, where the object is made the anode to strip away contaminants. They also caution that some metals, notably stainless steel and aluminum, are tricky to plate directly onto and may require a copper underplate first to ensure good adhesion, even at the DIY level.
And the actual DIY plating step, how does that work?
For the plating itself, they recommend using low voltage, even down to around 1 volt, for the best, shiniest results. Higher voltages tend to produce poor, burnt deposits.
Lower voltage is better. Interesting.
Yeah, for quality in this simple setup. The object to be plated is connected to the negative terminal and the pure nickel source, or another inert anode if you've already made your solution, to the positive. They describe dipping the object, rotating it, and repeating the process to ensure even coverage. Also noting that you need to periodically move where you clip the electrical lead to the object, because the area directly under the clip won't plate well.
Right, the contact point blocks the plating.
Exactly. The bubbles generated often provide enough natural agitation for small items, but an aquarium pump can help for larger setups just to keep the solution moving.
And afterward, does it need special treatment? Does nickel tarnish?
Nickel is quite stable at room temperature and generally doesn't oxidize or tarnish readily, so it doesn't typically require a post-plating passivation like zinc might. Polishing can enhance the brightness, though.
Okay.
The Instructable source even touches on modifying the finish by adding small amounts of other metal solutions like tin for a whiter finish or copper mixed with nickel for a very hard, matte dark gray deposit. Alloying right in the bath.
It's a great analogy for understanding the basic chemical transfer and the importance of cleanliness and current, but it really makes you think about scaling this up and the safety.
And that brings us to a critical point. While the DIY method uses relatively milder chemicals like vinegar, industrial nickel plating solutions are far more potent and the safety implications are severe. This is where the Safety Data Sheet SDS from Nano3D Systems for a specific nickel plating solution really drives home the hazards.
That SDS was frankly alarming to read. The hazard list was long.
It is, and it should be. It lists multiple very serious classifications for the specific solution described. These include harmful if swallowed, causes serious eye damage, may cause an allergic skin reaction, may cause allergy or asthma symptoms or breathing difficulties if inhaled.
Okay.
And then it gets even more serious. Suspected of causing genetic defects, may cause cancer, may damage fertility or the unborn child, and causes damage to organs through prolonged or repeated exposure.
Wow. Hearing those potential long-term health risks directly from the safety data sheet, like may cause cancer and may damage fertility, really underscores that we're talking about powerful industrial chemicals here, not just something you mess with lightly in your garage.
Absolutely. It highlights that the risks go far beyond just immediate burns or irritation. These are systemic and long-term health hazards associated with specific components in the solution. The hazard pictograms listed on the SDS are equally sobering. The corrosion symbol.
For skin and eyes.
Right. The exclamation mark, signaling irritant effects, skin and respiratory sensitization, and acute toxicity. And critically, the health hazard symbol, which specifically indicates potential for mutagenicity, genetic defects, carcinogenicity, cancer, reproductive toxicity, and damage to target organs. The signal word is danger, prominently displayed.
Danger. Doesn't get much clearer than that.
No. The SDS specifically calls out components like nickel the second bisulfamate tetrahydrate and nickel second bromide hydrate as having multiple severe hazards, including being suspected carcinogens and reproductive toxicants. Even boric acid, which is added to plating baths for buffering and stability, is listed for reproductive toxicity concerns.
This explains why industrial plating facilities have such strict safety protocols and require specialized training in ventilation and PPE. It's not just a suggestion. It's essential for protecting workers from really serious harm.
Exactly. The precautionary statements listed are extensive and necessary, requiring special instructions before handling, reading all safety precautions, strictly not breathing vapors or spray, washing thoroughly after any contact, prohibiting eating, drinking, or smoking in the work area,
Basic industrial hygiene, but critical here.
and mandating the use of extensive personal protective equipment, PPE, including impervious gloves, safety glasses or face shields, suitable protective clothing, and appropriate respiratory protection in environments where vapors are present. There are detailed first aid measures for every potential exposure route and instructions for secure, locked-up storage. It paints a very clear picture of the need for rigorous hazard control.
It certainly gives you a deep appreciation for the professionals who work with these materials safely every day. It's serious business. Given the complexity of the chemistry and process and the potential hazards we just discussed, it's not surprising that things can sometimes go wrong in electroplating. The sources detail some common problems encountered, many of which are relevant to barrel plating.
They provide excellent insight into troubleshooting. One fundamental principle that comes up repeatedly is that cleaning is absolutely critical, often cited as half the battle. You need to thoroughly understand the base material you're plating and the type of contaminants present to choose the correct cleaning cycle.
Back to cleaning again. It really is that important.
It really is. If parts aren't perfectly clean before they enter the plating bath, you're almost guaranteed to have problems. They recommend pre-cleaning excessively oily parts separately to avoid contaminating the main cleaning baths too quickly. Techniques like electrocleaning and ultrasonic cleaning are mentioned as aids to ensure surfaces are truly clean.
So if cleaning fails, what's the immediate consequence? What goes wrong?
The most common and frustrating result of poor cleaning is adhesion issues, where the plated layer doesn't stick properly to the base metal and peels or blisters, just flakes right off.
Peeling. Nightmare scenario.
Definitely. Peeling can also be caused by interruptions in the electrical current during plating, or if the bath temperature is too low for the specific chemistry. The sources offer a key diagnostic tip: examine the underside of the peeled layer and the exposed surface beneath it.
Like playing detective.
Kind of. If you see the bare base metal, the problem likely occurred during initial surface preparation or the very first plating step, like a strike layer. If you see an intermediate plating layer, like a copper strike, then the issue happened between that step and the final plating layer.
So the layer tells you when it failed.
Exactly. Maybe poor rinsing or an improper dip between baths caused it at that stage.
And speaking of rinsing, something as seemingly simple as inadequate rinsing or improper dips between different baths is a very common cause of contamination and subsequent problems like poor adhesion or poor finish quality. Carryover is a killer.
Beyond peeling, what other surface finish problems can crop up?
Several things. Pits. Those tiny voids or pinholes in the deposit can be caused by organic contamination or oil in the bath, trapped air bubbles due to insufficient mixing or poor part geometry, inadequate pretreatment, metal impurities in the bath, or chemistry imbalances like low boric acid content or low bath temperature.
Lots of potential causes for pits. Yeah. Solutions involve diligent filtration, proper agitation, bath maintenance, and strict process control. Then there's roughness or burr on the plated surface. This usually indicates solid particles in the plating solution.
Like dirt in the paint.
Exactly. This could be dirt, particles generated at the anodes, impurities precipitating out of the solution due to high pH, or contaminants from the makeup water. Filtration of the plating bath is the primary solution here, along with careful control of pH and current density.
What if the color looks off or it's uneven, blotchy or dark?
Dark or uneven color is often a sign of metal contamination in the bath, frequently caused by drag-out carrying metals from previous tanks, like copper from a copper strike bath contaminating a subsequent nickel bath.
Contamination again.
Minimizing drag-out is crucial, and sometimes electrolytic treatment, called dummy plating, can help remove metal contamination from the tank. Other causes include poor pretreatment or base coating, too low current density, a low concentration of the main plating salt in the bath, or poor electrical contact to the parts.
And burning. What causes that?
Coating burn, where the deposit looks dark, dull, or actually burnt, especially in high current density areas, can be caused by several factors. Insufficient boric acid, low concentration of the main metal salt, low bath temperature, too high current density for the bath chemistry, high pH, or insufficient agitation. Specifically, black burn in nickel plating is often attributed to a lack of sufficient boric acid. Adding boric acid to the bath is typically the fix.
Boric acid seems important for nickel plating.
It is, acts as a buffer, and helps with brightness and preventing burn.
Are there problems that are particularly prone to happening in barrel plating because of how the parts are handled, the tumbling and bulk contact?
Yes, the tumbling action and the method of electrical contact in barrels can introduce specific challenges. One issue mentioned in the Some Production Problems source is observing a double nickel layer, particularly when parts are bent or crimped after plating, causing the layers to separate. Looks like two distinct layers.
Why would that happen?
This is most likely caused by current interruptions during the plating cycle. In a barrel, the flexible danglers might occasionally lift out of the tumbling load, or there could be loose electrical contacts in the barrel's hanger assembly. Even a brief break in current can cause a thin, passive layer to form on the part surface.
So the plating stops, then starts again on a slightly oxidized surface.
Exactly. When the current resumes, a new layer plates on top of the passive one, creating a weak interface that can delaminate, appearing as a double layer. This is especially problematic in low current density areas of the barrel where contact might be less consistent.
That makes sense. What else is specific to barrels or new tanks?
Another issue, relevant when setting up new equipment, is cloudiness in new nickel tanks. If a new tank lining, often rubber or plastic, hasn't been properly leached beforehand, the plating solution itself will start to leach substances out of the lining over time, causing a milky white haze in the bath.
So the tank itself contaminates the solution.
Can happen if it's not prepared right. Testing lining materials for compatibility with the plating chemistry beforehand is important to prevent this.
Okay. And what about problems after plating?
A particularly frustrating post-plating issue, often seen with barrel-plated parts processed in bulk, is spotting out. This is discoloration or stains that appear on the plated parts hours or even days after they've been plated and stored. Looks fine initially, then stains appear later.
Delayed problems. What causes that?
It's frequently caused by tiny traces of process chemicals, like cyanide from certain pre-treatment dips or copper strikes, that weren't completely removed during rinsing and got trapped on the surface, especially in recesses or pores. When parts are stored in bulk and aren't completely dry, these residual chemicals can react with the air or moisture and cause staining over time.
So spotting out shows how crucial post-plating steps are, like rinsing and drying, especially when you have parts in bulk that might trap moisture or chemicals. Can't just dump them wet into a bin.
Exactly. It highlights that the process isn't over until the parts are clean, dry, and stable. Better rinsing, sometimes even needing part redesign for better drainage, and a final warm water rinse, maybe with a neutral soap, followed by thorough drying, can minimize this.
Okay. Any other quick examples of problems?
The sources mention other issues too, like a low plating deposition rate if the bath pH is too low or current density is insufficient, or issues with the anodes themselves becoming passive and not dissolving properly, starving the bath of metal ions. They also touch on challenges plating on specific alloys like leaded brass, which might require special acid dips before plating, or the impact of plating thickness on dimensions, such as increasing the pitch diameter of threaded parts. It's a complex ecosystem of chemistry, electricity, and mechanics where many things have to go right simultaneously.
It certainly seems that way. We've definitely taken a deep dive into the world of barrel plating, defining what it is, tracing its history back to wooden barrels, understanding its powerful advantages for high-volume production, exploring the detailed mechanics of the equipment and the art of selecting suitable parts, navigating the strategic choice between pre- and post-plating, getting specific with the nuances and safety hazards of nickel plating, and troubleshooting common problems.
Phew, that was a lot to cover.
It was. So how does understanding all of this connect back to you, the listener? Why should someone who isn't a plating expert care about the difference between a horizontal and oblique barrel or the function of boric acid?
Well, it matters because barrel plating is a foundational process for manufacturing countless metal objects that you see and use every single day, from the screws holding your furniture together to the connectors in your electronics, the parts in your car, the hardware on your doors, and even decorative items.
It's everywhere, even if hidden.
Exactly. Understanding barrel plating gives you insight into how a vast number of these common items acquire their critical properties like corrosion resistance, durability, and appearance. It helps explain why some items are cost-effective for mass production and what quality aspects are prioritized or perhaps traded off in that process.
It demystifies the finishes on everyday objects. Suddenly that shiny bolt isn't just shiny.
Precisely. And if you are involved in designing, specifying, purchasing, or simply using metal parts in a professional context, understanding the core principles, the strengths, and the limitations of barrel plating versus other methods like rack plating,
And pre versus post plated.
and the implications of choosing pre versus post plating, yes, it empowers you to make more informed decisions. You can ask better questions of your suppliers or colleagues. You can select the most appropriate and cost-effective plating process for a given application, balancing the required finish quality, part characteristics, volume, and budget.
Helps you be a smarter consumer or engineer.
Exactly. Finally, learning about barrel plating, especially seeing the details about the complex chemistry, the need for precise electrical control, the mechanical handling challenges, and particularly the severe safety warnings highlighted by the SDS.
Yeah, that safety part really stuck with me.
It fosters a deeper appreciation for the complexity and inherent risks involved in modern manufacturing processes. It underscores the critical importance of expertise, rigorous process control, environmental responsibility, and robust safety measures within the industry, regardless of the scale of the operation. It turns a simple plated surface into something far more interesting, with a story of innovation, efficiency, and careful execution behind it.
It really does make you look at a box of shiny screws differently.
Yeah.
Appreciate the journey they took.
It transforms the mundane into something quite technically fascinating, doesn't it?
It really does. We've reached the end of our deep dive into barrel plating, covering everything from its definition and history, the significant advantages it brings to high-volume manufacturing, the intricate details of the equipment and how it works, the specific world of nickel plating and its associated challenges and safety concerns, and the practical implications of this process for anyone interacting with plated goods.
As we wrap up, let's consider this. Given that barrel plating's core identity is rooted in high-volume efficiency, often involving bulk handling and the use of potent chemical baths, how will the industry navigate the future?
Good question. What's next?
How will manufacturers and equipment providers continue to refine this technique to meet the growing demands for ever higher levels of dimensional precision on smaller and smaller parts, increasingly stringent environmental regulations regarding chemical waste and air emissions, and enhanced worker safety standards?
When they do all that and keep it cheap.
That's the challenge, maybe through integrating more advanced robotics and AI for process control, or developing entirely new, safer chemistries, all while somehow preserving the fundamental cost-effectiveness that makes barrel plating so valuable today. It's a continuous push and pull between industrial-scale efficiency and the evolving technological, regulatory, and safety landscape, something to think about next time you see a plated part.